Hello, welcome back. Welcome to online learning. Welcome to remote quarantine COVID-19 education time. All right, we are skipping chapter 11. I know we'd learned some of it, but forget it. It's gone. We don't have to talk about it because it's not going to be on the AP exam. I might swing around after, the AP test and teach it. Ha! But I assume you guys might be digital learned out by about what is that, 15, 16, it's like May 19th or something when my 8 juniors return. So we're going to put 11 and 12 on the back burner. We're going to come around and hit chapter 3, the last chapter on the exam that we have yet to cover. Talking about scatter plots and correlation. Talk about describing relationships for a specific type of variable, quantitative variables. What can we do with quantitative variables? We can put them on a scatter plot. We can fit a line of best fit, a least squares regression line, to that data, and we can make predictions about that data. So that's what we'll be going. Response versus explanatory variables. This is our first thing. I like to write it as explanatory and response variables. Explanatory, that's what you called in science classes your independent variable. Independent. That is your IV. Often shows up on the x-axis. I very much prefer the name explanatory. What does the explanatory variable do? It explains things. What does the response variable do? It responds clearly. That's going to be your dependent variable. dv, going to show up on the y-axis. So again, this will be explanatory and response. And we're going to have to title these graphs. It's often going to be the effect of explanatory on response. Are you going to write the words explanatory and response? No, you are going to write the words in context. Thank you very much. All right, so determine the explanatory and response variables in each example. Take a moment to read through these. This would normally be a chance where I'd say, hey, talk to your neighbor, but you don't have a neighbor. So pause it. Think about it for a second. Thank you for pausing it. All right, your explanatory variable. In the next case, what are we measuring? How does drinking beer affect the level of alcohol in our blood? Okay, we got a limit. Drank different numbers of cans of beer. 30 minutes later, they measured their alcohol levels. Explanatory is the number of cans of our beverage. And the response is the blood alcohol level. What do I expect that looked like? Think about what that would be. Your explanatory variable, number of cans, that's a discrete random variable. 1, 2, 3, 4, 5, and yeah, we'll stop there. Blood alcohol level, that's a continuous random variable. It goes from 0 up to, I don't know, let's call that like, I don't know, point maybe 16 or something. There we go. So we'll call that 0.8, the legal limit, and 0.04, some states' legal limits. So great. That's interesting though. Noticing that one can of beer might have different blood alcohol responses from different people. Interesting idea. We're not going to get the same. Different people, different metabolisms might. What was it? Like per hour or something, whatever. Okay, but notice that we might have different responses for a single value of the number of cans consumed. So that's interesting. Or this is discrete, and this is continuous. A discrete explanatory variable can have a continuous response variable. Interesting. All right, and down low, National Student Loan Survey provides data on the amount of debt and their income and how stressed they feel. All right, what's our explanatory variable? Explanatory is income, maybe the income to debt ratio. Response What do we respond? How do we respond to income and debt? We respond to it with stress. Great. Cool. That one, I don't know how how do you measure stress? How is stress measured? So we got income and debt down here, and that's likely continuous. A lot of times stress is measured on like that 0 to 10 or 0 to 5 scale. So 0, 1, 2, 3, 4, 5. This might be a continuous versus a discrete case. So 0, 1, 2, 3, 4. Why did I put 0 above the x-axis? 1, 2, 3, 4, 5. Or that's 0 down there. So this might be a case where, lower incomes might have higher stresses. This is going to look kind of opposite of the last one, where all our dots are kind of on a horizontal line of the stress level. The stress level, higher income to debt ratio. You got more income than you got debt, you're less stressed. You got smaller amounts, more stress. There you go. So that's a couple different examples of what we might see when we're plotting this stuff. Remember, this is going to be quantitative variables, data that's got numbers associated with it. So let's keep moving. Take a look at the next page. You've seen this example before. This example at the top is our example that dealt with confounding and lurking. Take a look back at your 4.2 notes. You can find that we've done the parts B and C from this for confounding and lurking. And recall that since this is an AP example, we can always Google that along with the word scoring guidelines to find our answer. So this was an explanatory variable that had, I believe it was exercise status confounded with smoking status. And we said, well, why might those two be associated? Well, if you exercise a lot, you probably don't smoke a lot. And if you do smoke a lot, you probably don't exercise a lot. That's one of those variables in the background pulling the strings on the situation. Article report that a study tracked the medical histories of some men and women for 23 years. Good number of them, 21,000. Article stated that those who smoked at least 2 packs of cigarettes a day, the risk of developing Alzheimer's disease was 2.5 times the risk for those who did not smoke. What's the explanatory and response? Explanatory variable. Number of packs of cigarettes smoked. Cool. Don't vape, by the way. Let's just throw that out there. Vaping's bad. Got to get my vaping plug in there. You know why it's particularly bad right now? Inflames the lungs. You know what COVID-19 does to you? Inflames the lungs. If you got somebody that you think's got COVID-19, tell them stop vaping. Rant over. Response variable. What's our response variable? Somehow the risk of developing Alzheimer's disease. Probably harder to vape. Was it harder to vape secretly when you're at home versus at school? Do people vape in my trailer? Don't answer that. All right, so scatter plot. We're going to be making some scatter plots here. Scatter plots show the relationships between two what? Quantitative variables. Great. And so we've got this very nice plot here of age of husbands versus age of wives. There's an interesting line that we could put here. Coaster here, allow me to draw a straight line. I'm going to draw a line called the identity. This is the line where y equals x. In this case, contextualizing y and x. This would be the line where wife's age equals husband's age. Why have I drawn that line here? No, because everybody's below the line. Take a moment to consider, what does it mean for a couple to be above the line? What does it mean for a couple to be below the line? Oh, what does that mean? Okay, think about this. They're equal here. If I go down here, husband greater than wife. What's up here? Wife's age greater than the husband. What do we see? Ooh, interesting relationships. Husbands, typically older than their wives. All right, great. What's the explanatory variable here? Husband's age. What's the response variable? Wife's age. Cool. Cool. Don't need to belabor that anymore. Notice that we can often draw a line like that where one equals the other, and there might be some interesting things about that. When making a scatter plot, always, what do we need to do? I'll probably give it a good title, and probably give it nice, consistent spacing on axes, and also labels on there. Want to have consistent spacing on our axes. Also need to have labels on there. So, what else? XKCD cartoons, breaking up with people that don't label their axes. Yep, get them out of your lives. Okay, cool. Next page. What do we got here? Chance to make our very first scatter plot. Oh boy. Take a moment. Read through this question about number of undersea communications devices still working and the temperature of the water. Pause this. Work through this problem. Hey, thanks for pausing. Do you need some help? Let's give you a little help. Experiment was conducted to study temperature. Okay, temperatures done in a laboratory where the tanks were some different temperatures. After electronic devices were submerged in the tanks for 5,000 hours. Great. Is that important? I don't know. Each device was inspected to determine if it was still working. Cool. Following table provides information on the number of devices tested at each temperature and the number of working devices at the end of the test. And I have temperatures. So this is going to be my explanatory. Is the seawater temperature. But what's my response variable? What's my response variable? This is the tricky part. This is my help. It asks you to use the information in the table, construct a scatter plot that would be useful for showing the effective water temperature on the affected devices to work at least 5,000 hours. And a problem that I'm going to mention to you, look at the number of devices tested. Think back to that very first graph we ever made in this class, section 1.1, making bar graphs for ice cream preferences. And the boys liked everything more. Why did the boys like everything more? Because we talked to more boys. We need to do something if we don't have equal numbers. Pause again if you got stuck. Say, what do we have to do if we don't have equal numbers of devices? Hey, thanks for pausing. You got to come up with a proportion of devices working. What is 29 out of 30? That's 0.97. What's 42 out of 50? 0.84. 21 out of 30, what is that? Reduces, divide out of 3 is 7 out of 10, 0.7. 12 out of 20, divide out of 2, 6 out of 10, 60%. So it looks like as temperature goes up, these devices are less likely to continue working. Cool. That's a better comparison than the number. Just look at that. You might have said, oh, 30 is better than 10%. 30 degrees is better than 10 degrees because we got a bigger number. No! You got a smaller proportion. Check those relative frequencies, bruh. All right, so what do we have here? That's terrible. God, that's terrible. We have here the proportion of working devices. And we're going to have the seawater temperature. I'll sketch this out real quick. Can I get up to 7, 0, 10, 20, 30, 40? Cool. And proportion, I can't count by that. Got to count by what? Like 0.2, 0.4, 0.6, 0.8, and 1. Sketch this out real quick. 0.97 for 10. 10, 0.97, 30, 0.84, 30, 0.84, 50, 0.7, 50, 0.7, and 70.6, 70.6, cool. And we've made our first scatter plot. The trick there is dealing with the proportion of working devices as opposed to the count. How are we going to do these in our calculator? You can do this by putting your data into L1 and L2. We could have put that data on the previous page into a plot. Let's do it real quick. Get out your calculators. Oops, sorry about the glare. Put it over there. Hit stat, edit. You're going to edit some lists. I'm going to put 10, 30, 50, and 70 in L1. That's my X. That's my explanatory. And I'm going to put 0.97, 0.84, 0.70, and 0.60 in my Y, in my L2. Explanatory and response. How do I plot this? Well, go ahead and hit second, stat plot. We're going to turn plot 1 on. Going to select the scatter plot option. Notice it changed to X list L1, Y list L2. That's cool. Then go ahead and hit zoom. Whoop. If that ever happens when you hit zoom, just hit second quit. Then hit zoom again and hit zoom 9. Gets you your stat zoom. And look at that. We've got our plot. Very fancy. Cool. So we can do that. And you've got those instructions down below here. Continuing on. You remember socks? You remember describing distributions? Now we get to describe associations. And we're going to describe associations with this fun acronym. Fun. Haha. FODS. F-O-D-S. Or you can go with DOFs. Or you can go with, what else? You could just, stupid things. Soft. You know. Play with it. I don't care. Whatever. Whatever helps you remember it. What are these FODS? Those FODS are form, outliers, direction, and strength. Form, outliers, direction, and strength. Direction is a form of association here. So what is the direction? Direction. Is it going up or down? Is it a positive or negative association? Does it look like this? Or does it look like this? Is it going up? Is it going down? Positive association. As X goes up, Y goes up. Another way you could say it is large values of X go with large values of Y. Conversely, negative association, as X goes up, Y goes down. You could say large values of X go with small values of Y. Cool. When describing these characteristics, okay, be sure to use context. We're going to have to slap context on all this. Next thing we have to talk about direction. We can talk about form. The big answer for form is either it's going to be linear or it's going to be nonlinear. Linear form, you know what that looks like. Nonlinear form, there's a few different types of nonlinear forms. You might see, I don't know, what could you see? Might see quadratic. Might see, I don't know. Ooh, here's one from the news, boys and girls. What's this? What's that? That's exponential growth. If you wanted to, you could call these all kind of curved forms as well. But quadratic and exponential, like doubling time, like, I don't know, the number of infected people? No, it's not exponential forever, though. Eventually, it levels out. I got to show this to you because I started rambling about it. Why can't it grow forever like that? Well, because you got, like, resource restraints. So eventually you say, oh, there's not that many more people left. Oh, it starts doing something like that. Called a sigmoidal. Or an S-curve. Where this right here is something like carrying capacity or the population size. There's your fun thing. It's not going to be exponential forever. The growth of anything really can't be exponential forever unless it's imaginary, like, you know, problems in a book on some number of lemmings on the forest. I don't know. Whatever. Moving on. Fun times. Fun times. We're going to look at these scatter plots and we're going to see some points that kind of look weird. Sometimes they're outliers. Sometimes they're influential. Sometimes they're both. What's an outlier? You've heard the word outlier. Outlier lies outside the overall pattern. Great. That's what an outlier is. An influential data point is one, well, it has influence. An influential data point, the removal of such point has a large effect on the correlation and or regression. Call it influential. If removing it would have a big effect. Here we have an outlier. It lies outside the overall pattern, but its removal has little effect. So it is not influential. Taking that point away didn't have hurt it, because it was kind of with it fit the regression line, but it was far away in terms of the x direction. What do we have here? We have both an outlier and an influential data point. It's far away, down below. It's far away, and it has a great effect. This is like the fat man sitting on the teeter-totter. Way out on the teeter-totter. He has a great effect on the line. That right there. It's a fat man on a teeter-totter. It does not fit with the pattern. That's what the pattern looks like. This one out here pulls that teeter-totter way down. Get off the teeter-totter. Okay. We have outliers and we have influential data points down below. Take a moment. Let's use our FODS descriptors. Well, this is going to be a good chance for a FODS template. Let's do this together. Based on the scatter plot, describe the relationship between arm span and height for the 12 seniors. We measured some heights and some arm spans. What do I see? There is I forgot to talk about something on the last page. I got excited. Flip back. I forgot to talk about strength and outliers. Go back to that. We can talk about the strength of an association. Going to talk about the strength of the association. Let's do 1, 2, 3 of these. Strength is how well does the data fit to the prediction line. That is, how strong is the pattern. You might have a not very strong pattern. Weak. And in that case, we're going to have something called R, the correlation coefficient eventually. We're going to say R is less than, absolute value R less than 0.3. You might have something, I don't know. Something like that. Might have something moderate. Or moderately strong. Absolute value R between like 0.3 and 0.7. You might have something like that. Looks very strong. Call that strong. Absolute value R greater than 0.7. So we'll have weak, moderately strong, and strong relationships. And we also got to talk about outliers. What are outliers? They don't fit with the pattern of the data. They're far away. What do we have to do with all this? All this in context. Got to have context on all this stuff. So, with that in mind, actually teaching you the material before I try and ask questions over it, let's look at the next page. AP example talking about arm span versus height. There is well, let's look at that. Fit a line to that. I'd say there's a pretty strong, positive, goes up, linear association between height and arm span with no obvious outliers. If you wanted to call this guy an outlier, you could. I wouldn't be mad at you, but I don't think it's that obvious. So strong, that's my strength. Positive, that's my direction. Linear, that's my form. No obvious outliers. F ODS, SDFO. I don't care how you remember it, but that's the acronym I'm going to be using. So FODS. So that's a FODS template. It's an AP template. You're going to need this. Make sure you've got this. It's an important example. So AP example, you got one on the next page here for you. We're going to do the top one. The second one we're going to save for a review day. We'll come back to that later. Up top, asks us to talk about what is positive, what is linear, what does strong mean. Take a moment, pause it, we'll come back. Hey, thanks for pausing. What does positive mean? Positive means I as what? The length of wolves increases, we predict an increase in weight. That's one way you could say it. Linear, what does linear mean? I don't know, the data, the relationship shows a linear pattern. What does a linear pattern look like? A constant rate of increase in weight per length. And what does strong mean? The data points are close to the prediction line. Again, you can search this one if you Google researchers studying a pack of gray wolves in North America and say scoring guidelines, you will find the answer. So we're going to skip the next one about sewing machines. If you want to do that, you can. I'll come back to it. So I'll try and be done in the next 5 minutes. Don't worry. It's going to get this done for you. Correlation coefficient R. Correlation. What is correlation? Correlation, talked about this already. It's R. Is the strength and direction of a relationship between two quantitative variables. Here you got a formula that you will never use. Again, R can be positive. R can be negative. Positive R looks like that. Negative R looks like that. If your R is 0, what's that data look like? It's all over the place. If your R is 1, what does that look like? Perfectly positive. What about R negative 1? Perfectly negative. Cool. Some facts about R. Read those over. Correlation is always between -1 and +1. Negative or positive indicates the points lie close to a line. Only achieved is perfectly linear. What do we got here? It doesn't matter which is x and which is y. It only works for quantitative variables. The value of R does not change when the x and y are changed. Correlation is non-resistant. Means it's greatly affected by outliers. And it measures correlation. If we're using correlation, that means very specifically we're talking about a linear association. What does it mean? The correlation R is non-resistant. Outliers have great effect. What happens to R if you change your variables? Nothing. Why? R is unitless. Take a look at why R is unitless. X minus X, Y minus Y. When you square root a squared unit, you get the unit. The units will cancel. The units will cancel. There will be no units on R. Last page? Last page? No. Oh, we got a few pages left. We got some work to do. Sorry about this. It's going to be a long lecture. I'll try and get done in 5 minutes, though. Can R tell me how strong a curve relationship is? No. It's only for linear. Can R tell me if I have a positive association? Yes. If R is greater than 0. That is, if R is positive. And you can only find R with 2 quantitative variables. Take a moment then. You have R's on the next page. Take a moment to try and match up these R's with these scatter plots. Pause it. Put those 6 numbers on the page. Ooh, computer froze for me there for a second. 30 minutes without touching it. Put those on there real quick. Hopefully you've paused it. Hopefully you've now looked. This is negative 0.99, very close to the line. This is positive. What is this? Positive 0.9. This is negative 0.7. This is positive 0.5. This is negative 0.3. And that's what 0 looks like. You don't even know which way to draw the line in there. So, down below, find and interpret the correlation coefficient. What is the correlation coefficient? The correlation coefficient is R. Here we have R squared. How do you think we get from R squared to R? Well, R is the square root of 0.250401. What is that? .5. What is that? There is a moderately strong positive association between length and FCR. How do I know it was positive? If I take the square root of something, isn't always the answer always positive? I know it's positive because this goes up here. Positive. Cool. All right. Dun, 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 dun. Oh, good. Last 2 pages are calculator stuff. How to find R in your calculator. Okay. Well, first thing I want you to do, hit mode. Press up until you get to Stat Wizards. Turn that on. Stat Diagnostics. Turn that on too. All right. Once you've got that on, here I've got the steps. I'm going to do these steps for you. We're actually not going to use number 4. We're going to use number 8, linreg A plus BX. I'm going to use that. Why? Because statisticians are weird, didn't like the way mathematicians were doing it. So that's what we're going to be doing. Y with a hat on it. You haven't seen that before. We are going to store regression equation in Y1. You're going to see that. And by hitting the diagnostics on, like you hopefully have from that 30 seconds ago in the video, you can then get your R and your R squared. If you don't turn those on, you won't get R and R squared. Last example, I'm going to get this done by 35 minutes. Didn't want to take 35 minutes, but it happened. Sorry, it's split block. You got time. So, here are the lengths of some femurs and some arms for the Archaeopteryx. Great. It's some sort of dinosaur. Archaeopteryx. Somebody draw me a picture of an Archaeopteryx. I'll give you some bonus. Make a scatter plot. Describe what you see, and find the correlation for these data. Does it agree with your description in Part A? Okay. I'm going to show you how to do it in your calculator. You're going to copy that work onto the page. I'm going to describe some things out loud, and then we're going to be done with the notes. So I'm going to hit Stat. I'm going to edit. I'm going to put in L1, those femurs, 38, 56, 59, 64, and 74. L2s are humerus arm bone lengths, 41, 63, 70, 72, and 84. Great. Got the data in, second quit out of that. Second y equals to get your plot up. Plot 1 is on. Scatter plot, L1, L2. Zoom 9, and there's your data. Copy it. What do you need? You need some freaking, increments on the x and y axis. I don't have that here. So you can hit trace and you can hop around. But copy this graph down. What do I see? I'm going to just describe it. There is pause it and make sure you can write this yourself. Strong, positive, linear association between femur length and humerus length. Cool. Strong, strength, positive, direction, linear, form, There are no obvious outliers. Oh, cool. Your plot, which needs to be better than this, needs to be actually labeled. It'll look something like that. Find the correlation for these data? Does it agree with your description in part A? To find the correlation, we need to do linear regression on this thing. So I'm going to do stat, calc, go down to 8, linreg a plus bx, choose 8, x list L1, y list L2, frequency list, get rid of that, delete that, don't need that there. Store regression equation, we can do that. Go ahead and hit vars. Go over and choose yvars, choose function, choose y1. We're gonna stick the equation for this line into y1. Let's go ahead and calculate, and it's gonna do this all for us. Hot damn, we got an R value at 0.99. R equals 0.99. Yes, this indicates strong correlation. All right, there you go. So you're watching this video on Wednesday. That means homework 3.2 is due Friday, and there's going to be a quiz as well. That'll be coming up. I'll have more to say about that on Schoology. Look out for that quiz on 3.1. Homework questions can be asked and answered in the discussion board that I'll be starting on Schoology as well. As always, email me if you have questions. Have a great day.